Atoms are the building blocks of everything we see and touch. They are tiny universes with electrons orbiting a nucleus. Understanding how these atoms interact is crucial. It unlocks secrets about the cosmos. Atomic collisions, for instance, are fundamental processes. These collisions occur when atoms collide with other particles, such as electrons. Studying these collisions provides insights into the behavior of matter. This knowledge impacts various fields, from astrophysics to medicine. Algerian scientists have made significant strides in this field. Their work on atomic collisions is pushing the boundaries of our understanding. Specifically, their research on electron collisions with hydrogen-like ions has garnered international acclaim. This work is not just theoretical. It has practical applications in diverse areas. These areas include plasma physics, fusion energy research, and even our quest to understand the vast universe. One of the key tools Algerian physicists use is the close coupling method. Now, this might sound intimidating, but bear with me. Imagine trying to predict the path of a billiard ball after it strikes others on a pool table. It gets complicated quickly, right? The close coupling method does something similar, but for atoms. It helps us calculate the probability of different outcomes when an electron collides with an ion. This method is particularly useful for studying hydrogen-like ions. These ions, like hydrogen, have only one electron orbiting the nucleus. This simplicity makes them excellent models for understanding more complex atoms. By applying the close coupling method, Algerian researchers have made highly accurate predictions about these collisions. Their findings have been published in prestigious journals, such as the Journal of Physics, B. Atomic, Molecular, and Optical Physics. So why does all this matter? Well, the applications are far-reaching. Let's start with plasma physics. Plasmas are superheated gases where electrons are stripped from atoms. Understanding how electrons interact with ions in plasmas is crucial. This knowledge helps us understand stars, which are essentially giant balls of plasma. Then there's fusion energy, the holy grail of clean energy. Fusion reactors aim to replicate the process that powers the sun. This involves fusing atomic nuclei to release tremendous energy. Understanding atomic collisions is essential for controlling and optimizing this process. Finally, we have space science. Satellites and spacecraft traveling through space encounter various atoms and ions. By understanding how these collisions affect spacecraft materials, we can design more resilient spacecraft. This ensures longer, safer missions for our intrepid explorers. Section 4. Testing the model, the quest for accuracy. But how do we know if these theoretical models are accurate? That's where experimental validation comes in. Scientists around the world are working hard to test these models in laboratories. They use sophisticated equipment to recreate atomic collisions and compare the results with theoretical predictions. And guess what? The models developed by Algerian researchers have shown remarkable agreement with experimental data. This consistency confirms the robustness of their methods and highlights the significant contribution of Algerian scientists to the global scientific community. Section 5. Algeria's ascent in atomic physics. The impact of this research extends far beyond the scientific community. For Algeria, it represents a source of national pride. It showcases the nation's intellectual prowess on a global stage. This success inspires young Algerians to pursue careers in STEM fields, fostering a new generation of scientists and innovators. Moreover, this research can lead to economic benefits. By attracting international collaborations and investments, Algeria can establish itself as a hub for atomic and molecular physics research. This, in turn, can lead to technological advancements, creating new industries and job opportunities. The work of Algerian scientists in atomic collisions is a testament to the power of human curiosity and collaboration. By unraveling the mysteries of the atom, they are not only advancing our understanding of the universe, but also paving the way for a brighter future for Algeria and the world. Hey there, science enthusiasts! Welcome back to For Science Salah Lotfy channel, your ultimate source for groundbreaking discoveries from the Arab world. Today, we're diving into the incredible story of an Algerian research team that's shaking up the world of theoretical physics. First, let's take a virtual trip to Algeria. Picture a map highlighting Tlemcen, Saïda, Algiers, and Nama. These cities are home to the brilliant minds behind this revolutionary research. Meet Dr. Asma Bouchiki from the Theoretical Physics Laboratory at Abubakr Belkaid University in Tlemcen. She's the corresponding author of this groundbreaking study. Next up is Professor Dr. Mohammed Salawi, also from the same lab and affiliated with the École supérieure en sciences appliquées de Tlemcen. Professor Dr. Lazri Boumediene joins us from Dr. Tahar Moulay University in Saïda, collaborating closely with the Tlemcen lab. Then we have Professor Dr. Abdesamad Sekal, working at Urmer in Tlemcen, and also with the École supérieure en sciences appliquées in Algiers. Last but not least, Professor Dr. Mamar Bouhamoud, who splits his time between the Theoretical Physics Laboratory in Tlemcen and the University Center of Nama. Now, let's talk about their groundbreaking research journey. The study was submitted on February 24, 2018, revised on July 24, accepted on August 15, and finally published on November 30, 2018, in the Journal of Physics B Atomic, Molecular, and Optical Physics. This team is proof of Algeria's scientific prowess. United across regions, institutions, and specialties, they're pushing the boundaries of theoretical physics and making a global impact. Their work is more than just research, it's a testament to collaboration, vision, and national pride. Stay tuned for Science Salah Lotfy channel for more stories of Arab researchers changing the world. Don't forget to like, subscribe, and hit the bell icon for more inspiring content. In the heart of Algeria, a team of physicists are making groundbreaking discoveries. They are exploring the fascinating world of molecules. Their research could change how we understand the universe. The team is focused on electron-impact ionization. This process is fundamental to many areas of science. It plays a crucial role in fields like astrophysics and plasma physics. Their findings have far-reaching implications for various technologies. The Algerian physicists are studying two key molecules, methane and ammonia. These molecules are vital. They are found in the atmospheres of planets and interstellar space. Understanding their behavior provides insights into the universe around us. Methane, a simple hydrocarbon, is the main component of natural gas. Ammonia, a compound of nitrogen and hydrogen, is crucial in agriculture. Both are relevant to our daily lives. Electron-impact ionization is a fundamental process. It occurs when an electron carrying energy collides with a molecule. This collision can cause the molecule to lose an electron. The molecule then becomes a positively charged ion. This ionization process is crucial in many natural phenomena. It's key to understanding how matter interacts with light and other forms of energy. The Algerian team is studying this process in detail. Section 4. Specialized Geometries. Unlocking Molecular Secrets. The Algerian team uses advanced techniques. They employ specialized geometries in their research. These geometries allow them to study the ionization process with high precision. They can analyze the direction of outgoing electrons and ions. These precise measurements provide valuable data. They help us understand the dynamics of electron-impact ionization. This information is crucial for developing theoretical models. Section 5. Theoretical Framework. Predicting the Unpredictable. The team's work is not just experimental, they are developing sophisticated theoretical models. These models help us predict the outcome of electron-molecule collisions. They use advanced computational techniques. Their theoretical work is vital. It helps validate their experimental findings. It also provides a deeper understanding of the underlying physics. Section 6. Global Impact Algerian Science on the World Stage. The Algerian team's research is internationally recognized. Their findings are published in top scientific journals. This recognition highlights the quality of their work. It also showcases the growing scientific prowess of Algeria. This research has far-reaching implications. It can lead to advancements in various fields. This includes astrophysics, plasma physics, and the development of new technologies. The team's work is a testament to the power of international collaboration. Hey everyone, welcome back to the channel. Today we're diving into the microscopic world to understand how electrons dance with molecules. Buckle up, science enthusiasts. First off, let's set the stage. Imagine a high-energy electron zooming in and striking a methane, CH₄ or ammonia, NH₃ molecule. When it does, it knocks out one of the molecule's own electrons. This is called single ionization by electron impact, or simply the E2E process. You might be wondering, how do we make sense of this complex interaction? Scientists use analytical models based on quantum mechanics like the Born approximation and the Coulomb wave model. These help calculate something called the triple differential cross-section, or TDCS. It's a fancy way of measuring the likelihood of ionization, considering the energy and angles of the outgoing electrons. Now let's talk geometry. The researchers looked at two scenarios: coplanar symmetric, where electrons share similar energies, and coplanar asymmetric, where one electron hogs most of the energy. What's really cool is that the theoretical calculations matched up with experimental data almost perfectly. This gives scientists confidence that these models can be used to understand more complex molecular systems and even help design new technologies. But why should you care? Understanding these interactions is crucial for fields like space science, plasma physics, and even medical physics. It helps us protect against space radiation, improve fusion reactors, and refine radiation therapies. So next time you think of electrons, remember, they're not just particles, but key players in the drama of molecular interactions. Thanks for watching. If you enjoyed this deep dive, hit that like button, subscribe, and share. Imagine the universe as a vast cosmic ocean teeming with particles in constant motion. Among these celestial voyagers are electrons, tiny particles carrying a negative charge. They zip and zoom through the cosmos, occasionally colliding with other particles like microscopic billiard balls on a grand scale. These collisions, while seemingly insignificant, hold the key to understanding the very fabric of matter. One such collision, known as electron-impact ionization, occurs when an energetic electron slams into an atom or a molecule, knocking off one or more of its own electrons. This process, akin to a cosmic game of marbles, leaves behind a positively charged ion and a trail of ejected electrons. By studying these ionization events, scientists can glean invaluable information about the structure and behavior of atoms and molecules. Consider, for instance, the simple molecules of methane and ammonia. These ubiquitous compounds found throughout the cosmos serve as fundamental building blocks in the intricate tapestry of interstellar chemistry. By unraveling the secrets of electron-impact ionization in these molecules, we gain a deeper understanding of the processes that govern the evolution of planets, stars, and even life itself. The dance of electrons and molecules in an ionization event is a complex and chaotic affair. It's like trying to predict the trajectory of a dozen billiard balls after a powerful break. The electrons, propelled by their kinetic energy, interact not only with the target molecule but also with each other, creating a tangled web of forces that is difficult to unravel. To make sense of this subatomic ballet, physicists turn to mathematical models. These models, akin to celestial maps, provide a framework for understanding the intricate interplay of forces at play during ionization. By simulating these collisions using powerful computers, scientists can study the dynamics of these events in detail, revealing the hidden mechanisms that govern the behavior of electrons and molecules. However, even with the aid of sophisticated models, accurately describing ionization in molecular targets remains a formidable challenge. The sheer complexity of these systems, with their multiple nuclei and intricate electron configurations, demands innovative approaches and computational tools. Undeterred, physicists continue to push the boundaries of knowledge, seeking to develop ever more precise and powerful models to illuminate the mysteries of the quantum world. Imagine trying to predict the weather with only a basic understanding of wind and rain. It would be a daunting task, to say the least. Similarly, studying electron-impact ionization requires a deep understanding of the forces governing the interactions between charged particles. To tackle this challenge, physicists have developed a range of sophisticated models, each with its own strengths and limitations. One widely used model is the Born approximation, a mathematical framework that simplifies the complex interactions between electrons and molecules. This approach, named after physicist Max Born, allows scientists to calculate ionization probabilities with reasonable accuracy, especially at high-impact energies. However, as the energy of the impacting electron decreases, the accuracy of the Born approximation diminishes. This is where more sophisticated models, such as the convergent close coupling (CCC) method and the R-matrix method, come into play. These models, while computationally more demanding, provide a more accurate description of ionization dynamics, particularly at low energies where electron correlation effects become significant. Section 4. Methane and ammonia cosmic clues to molecular mysteries. Why focus on methane and ammonia? These seemingly simple molecules abundant throughout the universe serve as ideal testbeds for our theoretical models. Methane, with its 4 hydrogen atoms arranged symmetrically around a central carbon atom, presents a relatively simple structure for studying ionization dynamics. Ammonia, with its 3 hydrogen atoms and lone pair of electrons, introduces additional complexities due to its asymmetric geometry. By studying these two molecules in detail, physicists can refine their theoretical models and gain a deeper understanding of how ionization processes differ in molecules with varying complexities. This knowledge is crucial for interpreting astrophysical observations, where electron-impact ionization plays a critical role in shaping the chemical composition of interstellar clouds, planetary atmospheres, and protoplanetary disks. Furthermore, understanding the ionization dynamics of methane and ammonia has important implications for atmospheric physics. These molecules are significant greenhouse gases, and their ionization by solar radiation influences the chemistry and energy balance of our own atmosphere. Section 5. A new lens on ionization, unveiling the E2E reaction. Now let's delve deeper into the heart of electron-impact ionization with the E2E reaction. This specific type of ionization occurs when an incident electron collides with a target atom or molecule, ejecting not 1, but 2 electrons. The result? A positively charged ion and 2 free electrons, each carrying a portion of the initial energy and momentum. By carefully measuring the energy and momentum of both outgoing electrons, physicists can reconstruct the ionization event with remarkable precision. Think of it as a cosmic game of billiards where we analyze the trajectory and speed of all the balls involved to understand the initial impact. This detailed information provides invaluable insights into the electronic structure of the target molecule, revealing the energy levels and momentum distributions of its electrons. The E2E reaction therefore acts as a powerful microscope, allowing us to probe the invisible world of electrons within molecules. By studying this reaction in methane and ammonia, we gain a deeper understanding of their electronic structure and how it influences their chemical behavior. This knowledge paves the way for more accurate models of molecular ionization and a clearer understanding of the intricate dance of particles that shapes our universe. Section 6. Mapping the cosmos of collisions, geometries of impact. Imagine an archer aiming for the bullseye. The angle of the arrow, the tension in the bowstring, and even the slightest gust of wind can influence the final result. Similarly, in electron-impact ionization, the geometry of the collision plays a crucial role in determining the outcome. The orientation of the target molecule relative to the incoming electron beam can significantly affect the ionization probability and the energy and angular distributions of the ejected electrons. By studying ionization events at various collision geometries, researchers can create a detailed map of the ionization process, revealing the most probable outcomes for different impact scenarios. This detailed mapping of collision geometries is essential for developing accurate theoretical models of ionization. By accounting for the influence of molecular orientation, physicists can create more realistic simulations that better reflect the complexities of real-world ionization events. This, in turn, leads to a deeper understanding of the role ionization plays in various physical and chemical phenomena throughout the universe. Imagine a world far smaller than the eye can see. This is the realm of atoms and molecules, where electrons dance around nuclei. In this subatomic ballet, collisions are commonplace. One such collision, known as electron-impact ionization, plays a crucial role in various fields, from astrophysics to materials science. Electron-impact ionization occurs when a fast-moving electron collides with an atom or molecule, knocking out another electron. This process is fundamental to our understanding of how matter interacts with radiation. It dictates the behavior of plasmas in stars. It influences the delicate balance of Earth's atmosphere, and it even underpins the operation of advanced technologies like electron microscopes and radiation therapy. In this essay, we delve into the fascinating world of electron-impact ionization. We explore the intricate dance of particles during these collisions. We uncover the mathematical tools used to model these interactions, and we highlight the profound implications of this process on our understanding of the universe and its technological wonders. At the heart of electron-impact ionization lies a specific type of reaction known as the E2E reaction. In this process, an incoming electron, denoted as E, collides with an atom or molecule. This collision ejects an electron, resulting in 2 outgoing electrons, hence E2E. To understand this reaction, let's consider two common molecules, methane, CH₄, and ammonia, NH₃. Methane, the main component of natural gas, consists of a central carbon atom bonded to 4 hydrogen atoms. Ammonia, commonly found in cleaning solutions, features a central nitrogen atom bonded to 3 hydrogen atoms. During an E2E reaction involving methane or ammonia, the incoming electron interacts with the electrons in these molecules. This interaction can transfer enough energy to overcome the binding energy of an electron, knocking it out of the molecule. The result is a positively charged ion and 2 free electrons flying away. The study of E2E reactions provides invaluable insights into the electronic structure of molecules. By analyzing the energies and momenta of the outgoing electrons, scientists can reconstruct the momentum distribution of the ejected electron prior to the collision. This information unveils the intricate world of electrons within molecules, revealing their energies and how they are distributed in space. To quantify the likelihood of E2E reactions occurring in specific ways, physicists employ a concept known as the triple differential cross-section, TDCS. Imagine a target molecule bombarded by a stream of electrons. The TDCS describes the probability of finding one outgoing electron scattered at a particular angle and energy, and the other outgoing electron scattered at another specific angle and energy. The triple in TDCS refers to the 3 key parameters that determine the scattering probability: the energy of one outgoing electron, the scattering angle of that electron, and the scattering angle of the other outgoing electron. By measuring the TDCS over a range of energies and angles, researchers gain a comprehensive understanding of the E2E reaction dynamics. TDCS measurements provide a stringent test for theoretical models of electron-impact ionization. They serve as a benchmark for assessing the accuracy of calculations that aim to predict the behavior of electrons during these collisions. By comparing experimental TDCS data with theoretical predictions, scientists refine their understanding of the underlying physics governing these interactions. In the quantum realm, electrons are not tiny billiard balls but rather blurry clouds of probability, described by mathematical functions known as wave functions. The wave function of an electron, denoted as psi, contains all the information we can know about its state, including its energy and momentum. In the context of E2E reactions, we encounter 2 types of wave functions: qk, which describes the initial state of the incident electron, and qks, which represents the final state of the scattered electrons. These wave functions are solutions to the Schrödinger equation, a fundamental equation in quantum mechanics that governs the behavior of particles at the atomic and subatomic levels. However, solving the Schrödinger equation for complex molecules like methane and ammonia can be computationally demanding. To simplify the problem, physicists often employ the frozen core approximation. This approximation assumes that the core electrons, those tightly bound to the nucleus, remain undisturbed during the collision. Only the valence electrons, those farthest from the nucleus and involved in chemical bonding, are considered in the calculations. While the frozen core approximation simplifies the calculations, it still captures the essential physics of the E2E reaction. It allows researchers to focus on the interactions between the incident electron and the valence electrons, which are primarily responsible for the observed scattering patterns. Imagine a world governed by the laws of quantum mechanics. Here, tiny particles like electrons dance around molecules. These dances, known as electron-impact ionization, are fundamental to many fields. Understanding these interactions unlocks secrets about the universe. Electron-impact ionization occurs when an electron collides with a molecule. This collision can cause the molecule to lose an electron. This process is important in various fields, including plasma physics and astrochemistry. Studying electron-impact ionization is complex. It requires advanced techniques and models. By understanding this process, we gain valuable insights. We learn about the structure of molecules and the nature of matter itself. This essay explores the fascinating world of electron-impact ionization. To understand electron-impact ionization, we must first understand molecules. Molecules are made up of atoms held together by chemical bonds. These bonds result from the interaction of electrons. These electrons reside in specific regions called molecular orbitals. Molecular orbitals are described by mathematical functions called wave functions. Wave functions contain information about an electron's energy and probability of being found in a particular region. Imagine a cloud around the molecule's nucleus. The denser the cloud, the higher the probability of finding an electron. These orbitals determine how a molecule interacts with other particles, including electrons. During electron-impact ionization, the incoming electron interacts with the electrons in these orbitals. This interaction can lead to the ejection of an electron from the molecule. To study electron-impact ionization, scientists use a powerful tool called the triple differential cross-section, or TDCS. This tool is essential for understanding the intricate details of electron interactions. Imagine a game of billiards at the subatomic level where particles collide and scatter in various directions. The TDCS is like a map that tells us the probability of different outcomes after the collision, providing crucial insights. The TDCS depends on several factors, including the energy of the incoming electron and the angles at which the scattered electron and ionized electron emerge. These angles define the collision geometry, which is crucial for accurate measurements. Two important collision geometries are coplanar symmetric and coplanar asymmetric, each with unique characteristics. In the coplanar symmetric geometry, the scattered and ejected electrons emerge on opposite sides of the incident electron beam and in the same plane. In the coplanar asymmetric geometry, the scattered and ejected electrons emerge on the same side of the incident electron beam. By measuring the TDCS for different collision geometries, researchers can get a detailed picture of the electron-impact ionization process, enhancing our understanding of atomic interactions. Section 4. Matching Theory and Reality Insights from the Collision. Scientists have conducted numerous experimental and theoretical studies on the electron-impact ionization of methane and ammonia, aiming to understand the fundamental processes involved. These studies provide valuable insights into the intricacies of molecular ionization, revealing complex interactions at the atomic level. Experimental data, often obtained using sophisticated coincidence techniques, measure the triple differential cross-sections for different collision geometries, offering a detailed view of the ionization process. Theoretical models, on the other hand, aim to predict these cross-sections using quantum mechanical calculations, striving for accuracy. By comparing theoretical predictions with experimental data, scientists can assess the accuracy of their models and gain a deeper understanding of the ionization process, refining their approaches. For example, studies on methane have shown that theoretical models can accurately predict the triple differential cross-sections in certain collision geometries, but discrepancies arise in others, indicating areas for improvement. These discrepancies highlight the limitations of current models and the need for further refinement, pushing the boundaries of our understanding. Section 5. Beyond the Horizon, the Future of Molecular Ionization Studies. Electron-impact ionization is a complex process influenced by various factors, including molecular structure, electron correlations, and the energy of the impacting electrons. While significant progress has been made in understanding this phenomenon, much remains to be explored in this intricate field. Future research should focus on developing more sophisticated theoretical models that can accurately predict experimental data across a wider range of collision energies and geometries. These models must account for the intricate interplay of electrons within the molecule, which is often very challenging. Moreover, exploring electron-impact ionization in more complex molecules is crucial for advancing our understanding. This will contribute to our understanding of fundamental processes in various fields, including chemistry and physics. In conclusion, electron-impact ionization is a fundamental process that governs the behavior of matter in diverse environments, from interstellar space to biological systems. Continuous research in this field, combining experimental techniques with advanced theoretical models, is essential to unraveling the complexities of molecular ionization and advancing our knowledge of the quantum world. Welcome to For Science Salah Lotfy channel. In today's episode, we explore a fascinating study on electron-impact ionization of methane or CH₄ and ammonia NH₃ molecules. This research, published in the Journal of Physics B Atomic, Molecular and Optical Physics, Volume 52, 2019, Article 015201, spans 9 pages. It delves into how these molecules behave under both coplanar symmetric and asymmetric geometries. The study examines the detailed interactions when a high-energy electron collides with these molecules. By analyzing the collision in different geometrical configurations, the researchers were able to reveal the subtle differences in electron scattering, ultimately improving our understanding of molecular ionization processes. Their approach has tremendous implications for fields such as plasma physics, astrophysics, and radiobiology. Using advanced techniques and rigorous theoretical models, the research team compared their results with experimental data to validate their approach. The excellent match between theory and experiment speaks volumes about the precision of their methods and the depth of their analysis. Before we wrap up today's episode, I'd like to take a moment to express our deep gratitude for the outstanding work that made this research possible. A heartfelt thank you to Dr. Asma Bouchiki from the Theoretical Physics Laboratory at Abu Bakr Belkade University in Tlemcen, Algeria, whose leadership and expertise drove this research forward. Professor Dr. Mohammed Salawi, also from the Theoretical Physics Laboratory, Abu Bakr Belkade University, and the École Supérieure en Sciences Appliquées de Tlemcen, whose invaluable contributions helped refine the study. Professor Dr. Lazri Boumediene of the Theoretical Physics Laboratory, Abu Bakr Belkade University in Tlemcen, and Dr. Tahar Moulay University in Saïda, whose insights enhance the theoretical framework. Professor Dr. Abdesamad Sekal from the Unité de Recherche Matériaux et Énergies Renouvelables, ERMER, in Tlemcen, and the École Supérieure en Sciences Appliquées d'Alger for his critical role in the research. And Professor Dr. Mamar Bouhamoud from the Theoretical Physics Laboratory, Abu Bakr Belkade University in Tlemcen, and the University Center of Niamey, whose contributions were key to the success of the project. Your remarkable and distinguished efforts in this research have not only advanced our understanding of electron-impact ionization, but also raised the bar for excellence in theoretical physics. And a big thank you to all of you for tuning in today. We truly appreciate your support and passion for science. We'd love to hear your thoughts on this research. What do you think about the findings? And how do you see these insights impacting future studies? Please leave your comments below this video. Don't forget to like, share, and subscribe to For Science Salah Lotfy channel for more deep dives into cutting-edge research. Until next time, stay curious and keep exploring.